Hello, welcome to the SPAG video series. In this video, we're going to talk about configuring Unified MPLS Transport Service. So as you're already familiar with the network, in the network there are two access ring networks, one to the left and one to the right. The access nodes are R1, R2, R3, and R4. And we have the core network. The core edge nodes are ASR 9031, ASR 9001, ASR 9032, and ASR 9002. Looking at the unified MPLS architecture, there are two different things you need to design in a unified MPLS environment. One is the Igp design, and then one is the Bgp design. So first, talking about the Igp design. In the Igp design, we're going to split each and every part of the network into different Ospf processes. For example, here we are splitting the core into a different Ospf process, which is Ospf process 100, and we are splitting the access networks into different processes, which are Ospf process 300 and 200. So in an Igp design, what we have to do is we have to take a couple of things into consideration here. First of all, we are splitting the access networks into different Ospf processes so that we can reduce the amount of routes received on the access nodes. The access nodes, keep in mind, the access nodes are constrained in terms of the available memory and then the route storage capacity. So it's always good to constrain the amount of routes so that the access devices have only the required amount of routes necessary to get outside the access networks and then go through the core and reach the destination and access ring networks. So here, while configuring Ospf in the access devices, do keep in mind that in your lab, the core Ospf process 100 is already configured. So you need to configure Ospf process 200 and 300, which are part of the access networks on left and right. Now, since we are configuring different processes for each access network, remember the access networks will not have any idea about the core network and then the other access ring network. So we need to make sure we leak a default route into each access network so that if in most cases when the access nodes have to reach a destination outside the ring network, outside the local ring network, they need to have a default route to get outside the access network. And since we're going to talk about BGP for BGP to form BGP relationships, right? We need to redistribute the loopback of the ABRs, the area border routers, or the autonomous, or the I would call it the process border routers more in this case. So ABR is the most commonly used term. So the ABRs for the access ring network on the right side is ASR 9001 and 9002. You need to make sure you redistribute the loopbacks of these two ABRs into Ospf 200. The loopbacks of the ASR 9001 and 9002 would be part of the core Ospf process 100. And this is, again, like I said, to form BGP adjacencies between the access nodes and the ASR 9001. For now, let's actually just keep it that we need to form BGP adjacencies. We're going to talk about how to do the BGP design in the next section. There are a couple of other best practices also mentioned in this design. When you are mostly working with the customer, it's important these to keep in mind. So I have actually asked to configure prefix suppression also. This is to make sure that it further reduces the routing table in your access network. Only the loopback prefixes are going to be installed because those are the prefixes that you need to route the packets within the access or outside the access network. So using prefix suppression, what you're going to do is you're going to install only the host routes, and then you're going to advertise only the host routes. Ospf network point-to-point, I think this is pretty common known practice. So when you configure Ospf in the ring network that is between ASR 9001, R3 and R4, and 9002, So you're going to make it as a point-to-point. Don't forget the fact that you need to configure LDP as well in the network, because it's a part of LDP and then the BGP that the labels are assigned. So I don't want to go through every node into the CLI and look at the configuration, because that's going to extend the length of the video quite a bit. So here I have given a template of the configuration which talks about how you redistribute the loopbacks of the area border router into the Ospf process that we talked about. This is the Ospf process, and then you're redistributing the connected metrics, and then the connected one on the loopbacks you're filtering with the prefix set here. So in 903, the equivalent configuration is given. It's the same thing. You match the loopback with the prefix list, and then you redistribute the connected metric. Okay, so once that is done, what we're going to see is I picked up a routing table from R1. In R1, you will see that we have a default route that was originated, and then we see the default route, and we also see only /32 prefixes because we implemented prefix suppression. There are no point-to-point prefixes, and this is the loopbacks that was advertised. The loopback of ASR 9001 and ASR 9002. Simply we can put it as one ABR and the other ABR. Now jumping into the BGP design. In UMMT, you have to understand that the labels are assigned when you talk about end-to-end LSP path, the labels are assigned by BGP and then the LDP. Now, how do you configure BGP? So BGP design is pretty simple. You have full mesh, or you can do a router reflector-based BGP here in your core. And the ABRs for each ring, the ABRs which are attached to each ring, becomes the router reflector. And the access nodes becomes the router reflector client. And what you do is, when you are actually sending an update, BGP update from one router reflector client to another router reflector client, it's going to be reflected through the local router reflectors to the full mesh BGP in the core, and the full mesh BGP in the core is going to send the routes to the ABR on the other side, and the ABR is going to advertise it to the router reflector client remotely. In order to have full mesh BGP connectivity, make sure you implement next hop self on your router reflector to your router reflector clients. So that's pretty much about the BGP. Now again, talking about the BGP configuration is pretty simple and straightforward. You have all your BGP neighbors established. These are your BGP neighbors combining your the full mesh in the core, the BGP neighbors which form the full mesh in the core, and also the router reflector client. So if you see, I have the router reflector clients on ASR 9001. So I'll have a router reflector client 200.1.1.1. That's actually one of the access devices. Now, just looking at the same config on ASR 903, I have the BGP clients, BGP router reflector clients, which are my access nodes, and also the full mesh BGP. Now, you will also note that I have a command called send label for the neighbor, and you will see it in the BGP as well, the send label. The send label essentially, the labeled unicast of the send label essentially says that, hey, I'm using BGP to assign labels to you. I'm going to use BGP to assign labels to you. So once the BGP configuration is done, you have established your IGP adjacencies, you established your BGP adjacencies, and you have established your end-to-end LSP path. What you're going to see is you will see only the routes from your local access nodes as Ospf, and the routes from the remote access ring are going to appear as BGP. So BGP will assign the label, and they are going to transport it to the ABR. Right. So let me actually give you a quick example of this. So once you completed your UMMT setup, right? What you're gonna see is you're gonna see the BGP For example, let's talk about a route. Let's talk about a route which is advertised from R1 and R3 is receiving the route. So from R3, you will see a BGP label advertised by ASR9K1. So R3 will actually append or put the BGP label on and send it to ASR9K1 for the packets which are destined to R1. And again, ASR9K1 appends a BGP label and sends it to ASR903. The ASR903 will actually append a LDP label and send it to R1. So when you're seeing it, the labels which are actually pushed and popped are a part of LDP control plane and BGP control plane. It's just not LDP. So here with the unified MPLS, you must understand that we are trying to minimize the number of IGP labels, which are the number of IGP routes and IGP routes in the access networks. This is to keep the processing down on the access devices because they have relatively a smaller CPU when compared to the core or the edge devices. And we will use BGP to assign label because by having BGP, you will not actually employ as much as CPU power to recompute your path as much as you do in IGP. And then by eliminating or by segregating the IGP domains as well, you furthermore constrain your IGP calculations to only to the routes which are particular to that access domain. And you can, once you have established a unified MPLS, you can do an end-to-end ping from R3 to R1. 100.1.1.1 is the loopback of R1 and 200.1.1.1 is the loopback of R3. So I'm pinging the 100.1.1.1 using the MPLS ping, and my source address is 200.1.1.1. You could see that I can successfully ping, and further you can do a show MPLS forwarding, and then you can look at the label assignment in each and every hop. That will give you a good idea as well. This was unified MPLS. This is in fact you configured the unified MPLS transport. Now, since you have the transport infrastructure, if a customer is requiring E-line service, what you can do is you can configure a VPWS, and you can actually give the customer off, give the E-line service off to the customer. So the requirement of the lab 2 is you configure E-line service on R1 and R3, and see if you can connect the two CE devices that are connected to R1 and R3. You can transport any VLAN tag. In fact, I've kept the VLAN tag as 100. You can have any customer VLAN tag. But the essential part is with the unified MPLS transport, you have a more I would say process optimized and also scale optimized access networks, and you're greatly simplifying the operational complexity of your network. So when you're establishing the E-line service, your touch points are only R1 and R3. You just have to actually touch R1 and R3, and you don't have to really touch any other point of the network. If suppose even you're doing HVPLS sort of an implementation, then your touch points would be still considerably lesser when compared to your layer 2 based access network. So this is pretty much about the unified MPLS. I hope you have fun configuring unified MPLS tab, and I hope you have fun learning unified MPLS as well. Thanks for listening to the video.